Alright, so in this tutorial we're just going to go over the Born Haber cycle. I'm sure this is something that you've come across, and we're going to make it super simple for everyone to get it. So what is it? So basically, just like we can see before we even get to talk about the definition, we do know that sodium exists in solid state, chlorine exists in gaseous state. So when these react, they can give us what we are calling the sodium chloride, which is the anionic compound, right? But basically, this is not the actual process or the actual steps that occur for this to happen. So there are a series of steps that are supposed to happen to get to the formation of sodium chloride as an ionic compound. And that basically brings us to what we are calling the Born Haber cycle. So what is it? So we can define the Born Haber cycle to be a thermochemical cycle that shows the energy associated with each step in forming an ionic compound. So it's just a cycle showing different kinds of energy associated with the formation of an ionic compound. In this case, our ionic compound is sodium chloride. So basically, we're going to show all these steps, but before that, there are some key terms that we need to understand that are describing different processes that occur in a Born Haber cycle. So that's why we're going to start from. So beginning with first one, enthalpy formation. So what is enthalpy formation? So enthalpy formation is basically the energy that is associated to the formation of one mole of a compound or a substance from its constituent elements. So basically, all we are saying is if you're talking about the formation of sodium chloride as an ionic compound, so the amount of energy that is associated with the formation of one mole of sodium chloride from its constituent elements in their standard states. Basically, that is what enthalpy formation is. So in this case, we do know that the constituent elements of sodium chloride are first of all sodium and then chlorine, which we know exists naturally as what? Diatomically in gaseous state. So we need to make sure to say this is a single mole. So therefore, we cannot change anything on the right hand side, but we can change something on the left hand side to balance it out, because we know we have a single chlorine atom on our right, so we can put half there. So the energy associated with that is what we're calling the enthalpy formation. Okay, so we now know what the enthalpy formation is. So now the question is, in our calculations, did we expect it to be positive or negative as we talk about the formation of ionic compounds? Okay, so the basic idea is, if you go back to our Born Haber cycle, from what we are seeing is we are moving from a higher energy to a lower energy, so we can think of it to be an exothermic reaction. Okay, now the second part, what can we say? Ionization energy. What is ionization energy? So we can think of ionization energy to be the amount of energy that is associated with the loss of an electron. Okay, so when you have sodium has got capabilities of losing an electron. Okay, so it can lose an electron to give you, and of course that usually happens when it's in gaseous state. So think of it in gaseous state and then loses an electron, it becomes sodium plus and then plus an electron. So the energy associated with that is what we are calling what? The ionization energy. So of course we know this is not possible, but in a case where we have, let's say, first ionization energy of magnesium plus, there is also second ionization energy, which is going to involve the ion losing another electron, which will make it to be magnesium 2 plus. Okay, but I was saying for sodium that is not possible. So therefore, we cannot show ionization energy directly by just showing, say you're moving from magnesium and then you say directly to say magnesium 2 plus. No, we don't want to do that. We want to show them step by step, because we know energy associated with the first ionization and the second ionization are different. So that's what we're going to be talking about. So take note of that under ionization energy. So we've talked about ionization and also the enthalpy formation. And of course, I can add one more point on the first one. Enthalpy formation can either be positive or negative, but in most of the cases, as we will see, it's going to be a negative from our Born Haber cycle diagrams. Okay, Third point, atomization. What is atomization? What do you think of it when you say atomization? Of course, all these, we're talking about them in terms of energies. What are they? So, of course, we talked about ionization energy. So now what is atomization, first of all, before we get to define atomization energy? So atomization, basically, just as the term entails itself, we are looking at the formation of atoms from the molecules of a substance that we have. Okay. So formation of atoms is what we're calling atomization. So atomization energy basically involves or talks about the energy associated with formation of what? Formation of atoms. And what you'd want to do is think of atoms to be in gaseous states, because an atom cannot be a solid or a liquid. So we're just all what we are saying is, in simple terms, think of atomization energy to be the energy associated with the conversions of our substances from their standard states to gaseous states. Okay, that's why in some textbooks, if you have a solid, we can also refer to atomization energy to be sublimation energy. So you can think of this to be the same, where you have solid what? States. Okay. Now, what is the electron affinity? Now, electron affinity is basically the amount of energy that is released when an electron is being added to a neutral substance. Okay, so energy associated, or energy that is lost when a substance which is neutral is gaining an electron. Okay, so what is electron affinity? And then dissociation energy is basically the amount of energy that is associated with what? Dissociation reaction. So dissociation, we know, is when a compound is being broken. Okay, or basically what we can say is, think of a molecule that is the atomic. So think of oxygen, for example. If you get to break this into the atoms, okay, of course, 2 oxygen atoms, that is what we are calling dissociation energy. Okay, so that reaction is endothermic. Energy is required to break the bond. And then we can also think of lattice energy now, which is like the last one, the most important one. So lattice energy is basically the amount of energy that is associated formation of an ionic compound from the elements in their gaseous states. So now, the final process, which is like going to be the final process on this diagram, in this case where we are talking about our ionic compound to be sodium chloride. So where we get to have sodium in gaseous state reacting with chlorine in gaseous states to give us the sodium chloride that we are looking at. Basically, since these are in gaseous states, now the energy associated with the reaction there is what we are calling what? The lattice energy. Okay. So as we get to go down, we can think of it to be negative, right? And then if the opposite is also true, the breaking down of the ionic compound into its gaseous constituents is basically also lattice energy. Okay. So now we know all the steps or all the reactions associated with the Born Haber cycle. Now let's get to, first of all, finish this Born Haber cycle of sodium chloride as an ionic compound, and basically help us to even understand things more in details. Okay. So in summary, what did I say? Initially what I had said is this. I said we do know that in this reaction, or this Born Haber cycle, is just basically trying to tell us to say we have a reaction of sodium and chlorine giving us what? The sodium chloride, which is on the bottom as an ionic compound. Now, in the actual state, or in the actual process, basically, it's not direct as it is shown here. Okay, so there are a series of steps that are supposed to happen, or a series of processes that are supposed to happen for the actual reaction to happen. So now that's what we are talking about under Born Haber cycle. Okay, let's get to move now. So now, initially the states that we have, the natural states that we have are the ones that, right? So we have sodium and chlorine in their standard states. That's what we have. Okay. Now let's try to move. So what we expect to be the first step, first of all. What's going to be the first step? Because at the end of the day, what we know is the final state, or the final step that we want to see, is we want to see sodium, and this sodium is supposed to be in what state? So we're expecting to see sodium in what? In a gaseous state. And then we also want to see chloride in a gaseous state as ions. So that reaction there is what is associated with what? That is the lattice energy. React formation or energy associated with the formation of an ionic compound from the gaseous constituents. In this case, sodium and chlorine should be in gaseous states as ions for them to give us that ionic compound. Now, what steps must occur for us to get to a point where we have these ions in their gaseous states? That's what we want to talk about. So now, the first one, what we expect to happen is, first of all, we'll start first of all with a conversion of sodium to what? To gaseous state. So I can indicate something there. So go up, and then we're going to have a formation of what? Sodium in gaseous states. So sodium in gaseous states plus half the chlorine will remain as it is in gaseous state. So now, that kind of conversion from solid to gas, from the terms that we're talking about, what do you think? What process is that? We are moving from solid going to gaseous state. So you can think of that to be atomization. Another way to make it simple is you can think of that to be sublimation, because we are moving from solid to gaseous. So we can just say that is energy of what? So energy associated with that is sublimation. And of course, all these have got values. In most of the cases, they're going to give you a table to give you the value, the actual amount they are associated with sublimation of sodium. And then now we have our gaseous state. What else do we need in the next step? So in the next step, since for now we are still focusing on sodium, and we've seen that on our final step we expect to see sodium to be what? To be an ion in gaseous states. Not only should it be gaseous, it should also be an ion in gaseous states. So we can show that. So our next step, we want to see sodium in what? In that state as an ion. So we'll say sodium plus, since we know sodium of course is going to give us a plus because it's capable of losing a single electron, right? And then what else are we going to have? So I've talked about one thing, it's capable of losing an electron. So I'll say an electron has been lost, and then of course we'll continue to show the addition of what? Chlorine gas there. Okay, so now that's a very, very important step that we've shown there. So now, loss of an electron, what process is that? We are talking about it, where we have sodium losing an electron. So the energy that is going to be associated with that is what we are calling the ionization energy. So we can show it as delta H, and then we can put IE for ionization energy. So loss of an electron is basically ionization, right? Okay, can move a bit. Now that we have our sodium in the required state, what else can we have? Now, the reason why we started with sodium is because we know sodium is the one that is going to do what? Sodium is the one that is capable of losing because it is a metal. So after the electron is ready, we can now try to make chlorine to gain that electron, right? Now, before that gets to happen, what needs to happen is we need to first of all break down the chlorine from the atomic form that in which it is in this case, right? So let's do that. So our step is going to involve the breaking down of the diatomic. So we can't basically show gain of an electron by a diatomic substance. We have to show it first of all. It's supposed to be broken down into atoms, right? Okay. So of course, that energy we can refer to it as we talked about it to be dissociation energy, right? So we're going to have our sodium ion that we already have, right? So our sodium ion that we already have, and then what do we have? It's in gaseous state, of course, and then we have an electron that was lost by the same ion. Now we want to convert our chlorine, which is the atomic, we want to break that up. So what is dissociation energy? So we'll break that one up, and when we break them up, they're going to be 2 chlorine atoms in what? In gaseous states. Now there's a coefficient there of half. So if you multiply half by 2, it's going to give you what? 1. So we're just going to have a single chlorine. Okay, and that's a very, very important step there. So I can even show a line. I can show a line there. So at that point we are we are done. Why? Because we now know if this chlorine gas, which is of course in an atomic form there, if it gets to gain that electron, it's now going to give us what? The chloride ion that we are seeing there, and then the electron is going to disappear because it is gained by what? The chlorine gas. So this is a very, very simple diagram that you can summarize in your own way. By first of all, just thinking of it to, first of all, you have the ionic what? Ionic compound, and then first of all, what you expect is you want them to be in their gaseous ionic form, because that is what lattice energy is associated with. And from there, first of all, you want to first of all convert your metal to an ionic gaseous form, and then you get to convert the non-metal as well, so that it gets to gain the electrons that are coming from the metal. Okay, so I think we can talk about one more example as well, another diagram that is also showing a different kind of process on the same, so that we get to see what we are going to have. Right? Okay, so in this example, we're going to look at the formation of calcium chloride. In case they ask you to draw the table that is showing the formation of calcium chloride as an ionic compound, right? So of course we expect calcium chloride to be on the bottom there, right? This is a solid ionic compound. So I want you to think smart about it. I don't want you to just do it anyhow. I want you to be smart about it. First of all, we expect that on our right hand side, what we have should be what? So we should have energy being shown, right? So we have energy. Increase in energy going up. Now, one thing that we need to understand is, like from what we've seen, is we expect lattice energy to be associated with what? Formation of this ionic compound from the solid states, right? So from the gaseous state, that is, sorry. So therefore, I can show calcium, this side, I can show calcium 2 plus reacting in gaseous state with 2 chlorine atoms, 2 chloride ions, of course in their ionic form as well, gaseous. So those guys should react to give us what? To give us this. And of course the energy associated with that is what we're calling the lattice energy. So now, that's a smart way of thinking about it. So if you know, first of all now, the initial starting point of this is they need to start from their standard states. So calcium exists as what? So expect calcium to exist as what? As a metal in solid state. And then chlorine, of course, exists diatomically as what? In gaseous states. So, of course, the direct summary of this reaction is arrow going down, right? To give us that. So, that arrow is demonstrating or showing what we are calling the enthalpy formation, right? From the natural states. So, we can show that. So, this is the enthalpy formation. Okay. So enthalpy formation is showing the direct formation of the ionic compound from the standard states of the elements that makes it up. And these are the two simplest steps that you can show. And now from there, what you're trying to think about is how can you convert the solid to that and that gaseous to that as well. And those are the steps that are going to come upwards there. Now we said before you could convert a non-metal to that form, it needs to gain electrons. Now the source of the electrons, where are they going to come from? The source of electrons are going to come from the losing of what? The losing of a metal. Now this metal or solid calcium can only lose when it's already in what? In gaseous states. So what are we supposed to do? What can we do at this point? So we'll say, let's first of all convert our calcium to what? First of all, convert our calcium to gaseous state. So we can say, on our next step, we have calcium in gaseous state. And then we have chlorine, which is still the atomic. Okay, so that energy associated with conversion from solid to gaseous, we can refer to it as sublimation, or think of it to be atomization. So we can put delta ATM or sublimation if you want. Okay. Let me just use a different color so that we don't mix things up. So enthalpy of atomization or sublimation. Okay, so we are ready at that point. What else can we do? In this case, I'm going to consider first of all chlorine, first of all breaking down or dissociating. So what we have is we have chlorine existing diatomically, so we are breaking that bond. So the moment we break that bond, what do we expect to have? We're going to have two chlorine atoms, right? So I'll indicate that. So we have two chlorine atoms after breaking down what? After breaking down the bond. So it's no longer existing diatomically. And then our calcium is still in gaseous state, right? Okay. So what energy is associated with that? So we are referring that to be also the enthalpy of atomization, because we have formation of what? Chlorine atoms from the diatomic form of what? Chlorine. Okay. That's very, very important for us to understand. So we can now move. Our next step is now going to summarize the most important part. In this case, we need now the electrons. So these electrons are going to come from the metal. So calcium is capable of losing up to 2 electrons. So just show it directly. Calcium 2 plus, and then we have 2 chlorine gaseous atoms. Okay, very important and very simple. Now, one thing that we need to understand is at this point, the fact that we are moving from calcium to 2 plus tells us to say there are 2 ionization energy associated with that. There is ionization energy 1 for the loss of a single electron, and then also ionization 2. So if I want you to perform calculations, they are going to give you both values. Okay, and then now from that point, what do you expect to have? Now we expect that the chlorine atoms are going to gain what? The electrons. So if it gets to gain, this is now where you get to drop. Now they are not going to be negatively charged because we have gained the what? The electrons. And of course, I'm supposed to show the electrons there because we have loss of electrons. So those electrons were coming from the calcium metal of the calcium gaseous form. So those electrons are now gained to give us what? To give us the chloride ions there that are in gaseous state as negatives. Okay. So why 2? Because of the 2 electrons. That's very, very simple. Now, what energy is associated with this? So these conversions from the gaseous, gaining the 2 electrons. So gaining of electrons, what is process is that? So that is electron affinity, which we can show just by EA, right? So electron affinity. So these are all values that you're going to be given in your calculations. So lattice energy, enthalpy formation, sublimation, atomization, ionization energy 1, and ionization 2. Now in summary, what I want you to understand is, if we are to draw a sign here, of course a clockwise is arrow there. This is the way clockwise moves. So what you're going to notice is everything here is moving what? In the clockwise direction, except what? Except the enthalpy formation, which is going on the bottom. So all these are agreeing with this direction. This is also clockwise direction. Going up is clockwise direction. The only side is this side, which is anti-clockwise. So therefore, enthalpy formation is always going to be equal to the summation of all these other energies on this diagram. And that is the summary that I want you guys to know. Enthalpy formation is always going to be equal to the summation of everything else on the Born Haber cycle. Okay. So with that kind of an understanding, it's going to be very easy for you to perform calculations where we've already drawn for you, knowing that it is only the enthalpy formation which is anti-clockwise. So it is equivalent to the summation of all the other energies on the diagram. And one way of also remembering is, you know that the enthalpy formation is basically the summary of the actual process, because all what you're having is, you are having the reaction of the substance themselves in their natural states to give you the ionic compound. So if you go to a diagram, this is what we're saying. All you're having, all these processes that are shown up are just summarizing the reaction of calcium and chlorine to give you that. So that's why this energy is equal to the summation of all these other processes, because they are all leading to that. And basically, this is the basic idea about this Born-Haber cycle. It's very simple. It's not as complicated as they make it look. So just make sure you check out for the next video that is going to deal with examples and how we can answer some questions on the Born-Haber cycle. So thank you very much for watching. Hoping you now understand the Born-Haber cycle.